Good morning, students. Welcome to the mathematics class. This is first time in this entire session I'm coming in front of all of you. So I hope you all are doing well and have performed well in the last unit test. Now, after the completion of your unit test, we are moving towards the completion of the half-yearly syllabus. There, already you came across the application of derivatives. And this is, today we are going to start integral calculus. Students, you have already came across the differential calculus till date. And integration is one of the most important topic and one of the base of the calculus present in your syllabus. So, let's start our class. Fine? Now, as you can see, the heading I have written integration. What comes first into the mind of yours when you heard this word integration? Integration, collection, making certain things together, accumulation, so many synonyms were running across your minds. What about mathematics? What about calculus? Fine. So you have already seen calculus in a way of differentiation, where you have calculated the rate measures. You have seen a function fx changing with respect to a independent variable x. Fine. Now, after that differential calculus, we are stepping into integral calculus. How they are different, how they are connected, let us have a clear idea of that. Now, I wanted to say one thing, starting from the word came into my mind, accumulation. Here I have written accumulation. Students, you have already came across certain graphs of distance time, speed distance, or areas. Correct. Now, making out of it. For example, today all of us are very much busy in online classes. Or what you are doing? You are downloading something, maybe a class, online class taken by your teacher, or you are downloading a movie. So what are you doing actually? What are you doing? Suppose we have a graph where you have a comparative study of a download speed with respect to time. Then what are you doing? As you are downloading, you are collecting some data in your mobile or your laptop with respect to time. That's a process of accumulation. So you are accumulating the data. As time goes on, as your download speed, accordingly, you are getting some more and more and more MBs, KBs, GBs, whatever. So, here suppose there is a graph and you are stopped at this point, starting from the 0 seconds, and this particular block I have shaded for you. It is the accumulated data, isn't it? Whenever there is a force distance comparison, you are applying a force and something is moving out, some body is moving. So what are you doing? You're doing a work. So this particular block is giving you the work done by you or by any other external material, isn't it? Now, what is the base of this concept? That means within particular second, this is the area you're having in this number line. After another second, this is accumulated with the previous one, and this particular process moves on. And if you are asked to find out the data accumulated or the work done using your mathematics, you will simply apply the area of the rectangles, squares, or maybe any other shapes and size whose area is known to you. Now, why then this integration of a function so clumsy that an entire field is been made for you? Now let's understand that. Tell me one thing. Do you ever always find the download speed is same with you? No, isn't it? Do you always find you're running a car or a bike or a cycle? Always do you move in a constant way? Never. Imagine a sine curve. Is it always in the same way? Going up or coming down? Never. So, a function. So this is a function fx whose graph is twist and twirls. Suppose from that twist and twirls, I have taken a portion of a graph from A to B I have taken. And now you are asked to find out the area of it, the area under the curve. Now what are you going to do? Well, the quick idea comes, this particular, say from A to C, that doesn't give you a shape which is known to your syllabus. So what you will do? You will draw a particular line here. You will make two rectangular strips and you will write the total area as this rectangular strip plus the shaded area. Isn't it? Now this is our example. You can have many more twists and turns within this region. Now what will happen? We are still not knowing about the shaded area. This is not a known curve to me, known area formula to me. So what the next thing we have done? We have tried to minimize this portion whose area is not easy for us to calculate. Am I clear about it? So for that, what I did, I tried to make it short. So in that case, you will see, if I'm going to increase the number of lines here, the number of rectangular strips are going more and more. And if I go on moving with the process, actually what am I doing, children? This was the earlier figure, when I was having the length of one rectangular strip as like this, and I'm putting some more on it. So I'm getting the rectangular strip size like this. Someone will make it like this, someone will make it like this, and it will be lesser and lesser and lesser. The more minute strips you are going to make, the lesser shaded areas will be there. Understood? Just have a look on this. This is manually made. Imagine more and more fine lines. Don't you feel a decrease in the shaded portion? I know you can find that. And you understood my point also. The concept is now, I think, very clear in your mind. So, what I'm going to do? Previously, the area was A1 plus A2 plus shaded area. So, what I'm doing? I'm making more and more strips. And this area, the shaded area, is going negligible. Isn't it? So just have a look on this. The one expression I have written for you. This is the summation sign. I have not yet reached the integration sign. Remember that. Okay. Summation sign. Statistics, you remember it very well. Summation. I 1 to n. What is I? I is the total number of strips. Say a finite n strips I have made. And what is this particular expression tells us? Area of rectangle. Length into breadth. Now, in a particular rectangular strip, I hope you understood. This is going to be the breadth and this is going to be the length. So, length into breadth. Length into breadth. Now, imagine this one. Length into breadth. Length into breadth. Length into breadth. So, they are all in the multiplied form with the summation sign at the end. And the most important thing, limit delta x tends to 0. This is very important. The strips were made as small breadth, as minimum width as possible. That is limit. Whenever we are running to 0, limit comes first into our mind. Fine. So, delta x moving to 0, rushing to 0. And this is going to give me the area, the total area, the accumulation of certain data. The accumulation of this entire region. Understood? So, this is the beginning, and this particular formula has given birth to the definition of integration calculus. Now, this entire thing is written with a sign. Yes, integration sign. And the delta x. Say I have taken from A to B. I have limited myself to a particular portion of the curve. So when it is limited, then it is a definite integral. And when it is not limited, this is indefinite integral. So you have two branches under integration. Fine. So this is what we say calculation. Now how it is related to the derivative? You all have heard that this is even known as antiderivative. Now, so why this particular concepts come? What you have done in differentiation, when you have studied about the definition of the derivative, remember limit h tends to 0 or delta x tends to 0, a small, that is delta y by delta x. You remember all of you? Okay. So, there also delta x was tending to 0. We are doing the splitting and we are studying the graph with respect to a independent variable. The study of a dependent variable with respect to a independent variable. Isn't it? And there was splitting and there was a gathering. So two different concepts. And this is the entire, this relationship has given a birth to this entire calculus. Okay? They are joined with each other, as we won't consider a coin if it is blunt at one space and you have only a head, you don't have a tail. There is no meaning of that particular coin. Am I clear? So they are also interrelated with each other. Remember children, always, this is the most important thing that I am going to tell you. That is, after doing this particular calculation, you are suppose going to get a function, say fx, and you will find that the derivative. This is integration of fx, the small function. The integration of fx is capital Fx. The integration of fx is capital Fx. And the derivative of fx say for example, if it is f dash of x, say for example this is f dash of x, then what it is? Then what the relation we are going to get there? Let's study there. What I was saying, that integration of fx, if it is capital Fx, then the operator of d dx of on that integration sign operates as a cancelling out the being a antiderivative. So this is derivative is antiderivative, and see how it is going on, taking d dx on both the sides. So d dx of this one, d dx of this fx. So this is, these two operators are cancelling down, and this is fx. And d dx of fx we all know. So how we speak? See, if integration of fx is capital Fx, then derivative of capital Fx is going to be small fx. I will give you some examples of it also. Just remember, this integration is even known as antiderivative. Now let us take an example. We all know that derivative of sin x is cos x. Derivative of sin x, and this is cos x, the denominator goes there, taking integration sign on both the sides. Now again the same thing happens. Now look students, what we are getting. Here is the first formula you people have to remember. That is, integration of cos x dx is sin x. Now a very important thing you must have noticed while giving the answer, there is a presence of an integrating constant c. What is that c comes from? What is the use of such c's? We have never used such things in the case of derivatives. Now please look at the same example I have done here. Derivative of sin x is cos x. Now imagine I am doing derivative of sin x plus 3 is cos x. Do you find any difference there? No, because derivative of 3 is 0. We all know that. So definitely the answer remains constant, that is cos x. Then same process goes on. With the introduction of 3, there is again the same formula comes down, that is integration of cos x dx is sin x plus 3. And how can this be happening? So without 3, the same formula, with 3, the same formula. So if you wish to apply any constant, say 3 or 30 or 300 or anything, don't you think so that the effect in the formula will be nothing, because the derivative of a constant quantity is 0. So we never forget to put this particular integration constant in the case of indefinite integrals. Okay students, so we will be always applying this particular constant c with all the integration answers. Now again, this was cos x. Similarly, we can see the derivative of cos x, which happens to be minus sin x. So, now the formula which arises is cos x as I hope it is clear what I did. The denominator goes there. I am taking integration on both the sides. Can I do one thing? You won't, I hope, mind. I am putting this minus here and rest is there. Now, the question comes. What will be the integration of sin x dx then? Yes, it is minus cos x. It is minus cos x, but with a plus c, with a plus c, with a plus c. I hope it is clear to all of you. So now we've remembered that integration of cos x is sin x plus c. Integration of sin x is minus cos x plus c. Now, in the similar manner, I will be providing you the list of all the formulas which is present related to the integration. So, start learning from now. We are going to progress with this particular topic. And for example, if I am interested in some another function, say, for example, what is the derivative of log x? We all know it is 1 by x. So, with the concept of antiderivative, let us see that integration of 1 by x dx, from now we will remember, and since you will find somewhere this particular mod sign is applied there, so that means the domain is known to all of us that x is always greater than 0. So, this is another formula. Similarly, if it is e to the power of x, so now you understood, no? How easy to remember all the formulas of integral calculus if we know the formulas of the differential calculus. This is what I wanted to tell you all. So, it's remains same. The basic formulas. Fine, I'm going on writing all these formulas. See, now, say if it is, then how can we recall that whose derivative is secant square x? Whose derivative is secant square x? You're absolutely right. That is of tan x. That is of tan x. So we can recall that integration of secant square x dx is tan x plus c. Now can you tell me that what is integration sec x tan x? Yes, that is because derivative of sec x is how much? Derivative of tan x is secant square x, then derivative of sec x is how much? It is sec x tan x. Similarly, derivative of cot x minus cosec square x, derivative of cosec x, and you can find out the formula so easily, isn't it? Now, one more thing. You can derive, that's also very easy. This is derived from where? X to the power of, derivative of x to the power of n, remember. It is always n into x to the power of n minus 1. So from there, you can derive this formula again. Now look at this only. I wanted to tell you something about it. Look at this particular formula. If it is x to the power of 0, that means I wanted to say it is 1. See? If it is 1, that means it is x to the power of 0. So, always remember, It is x. Why? Because 0 plus 1 by 0 plus 1. So from now, you should all remember integration of dx is x plus c. Integration of dx is x plus c. So in the case of derivative, whenever we are finding out a derivative of a polynomial, say x to the power of 99, what it comes? 99 into x to the power of 98. But if it is, say x to the power of 99, it becomes 100. It increases, it integrates. It integrates. Doesn't reduce, doesn't differentiate, it integrates. So students, that was just an introductory class of integration. We have lot more to progress with the particular topic, and we will be doing so. I will be providing you the list of the formulas. Start learning from now. Keep one side the differential calculus formulas and one other side of the integration calculus, and I hope you understood the concept, what I tried to make you people understand. So, that's all for today. Practice well.